hear me and you can see me, okay. Thank you very much. Okay, perhaps we can start now. Okay. Good time of the day, wherever you are, and welcome to IATA Digital Aircraft Operations webinar. It's 8:04 a.m. in Chile, Montreal, in Canada, from where we are broadcasting the day one of our webinar at IATA headquarters today. Let me introduce myself. My name is Irina Homenko. I'm Manager of Operational Efficiency Tech Ops at Operation Safety and Security Department at IATA. I have been with IATA for 11 years doing various projects in the area of aircraft maintenance. Before that, I worked for Aerosvit Airlines in Ukraine as a head of cost and ops efficiency department at Airlines Tech Ops division for almost 7 years. And before that, as an economist at various airline roles. I hold a master's degree in economics. I'm currently getting a bachelor's degree in aerospace engineering. And just a second, I'm trying to change the slides. Sorry. Okay, you should be seeing our next slide now. It would be natural to let those of you who are not very familiar with IATA just very briefly to know who we are. So a very quick slide on who we are. IATA is the global trade association of world's airlines. It is comprised of 290 passenger and cargo member airlines, and it represents 83% of global air traffic. We have a head office in Montreal, Canada, and as I like to call it, a mothership, and executive offices in Geneva, Switzerland. We also have our regional offices in Amman, Beijing, Madrid, Miami, and Singapore. For today, there is a great high lineup of the speakers on our webinar's agenda, both internal and external. And before moving to our first section, I would like to mention a few details about our webinar logistics. We have designed this webinar as a blitz session of presentation to give you a bit of the taste of IATA and what IATA has been currently working on. For this reason, we will be welcoming your questions into the question section of this online tool. However, we will not have the time and opportunity to answer them today. Instead, we will collect your questions and we'll have them answered by our subject matter experts later. The file with the questions and answers will be sent and distributed to all participants in an email after this webinar. The participants will also receive a link to the recording of this webinar, which could be shared publicly. And now, straight to the topic of our webinar. Digital Aircraft Operations Initiative appeared at IATA around 10 years ago as a response to the fast development of the technologies and the drive for efficiencies and cost savings. Increased passenger traffic and abundance of the offered PSK had to be duly balanced by innovations and cost reduction in order for airlines to stay competitive. What you will see today and tomorrow is not an exhaustive list of IATA activities in this area. Moreover, we are conscious of the fact that there are many more activities out there carried out by our airline members, our partners, and other industry players. IATA's motto is to lead, serve, and represent the airline industry. We're carefully listening to our airline members and strive to help them in doing their businesses easier and more efficiently. On the picture, you see 4 areas of activities where IATA has been actively engaging with industry stakeholders and has achieved tangible results. Without further ado, now we will start the flight operations track of this webinar, and I'm delighted to introduce you to my colleague, John Sinnott, who is today with me in the office. John is a senior manager, flight operations and at Operations Safety and Security Department. He is IATA Secretary to the Aircraft Performance Task Force, Standardized Computer Aircraft Performance Task Force, and Digital Aeronautical Data Exchange. Also, Technical Advisor to ICAO Information Panel, ICAO Obstacle Limitations Surfaces Task Force, and Trusted Reciprocity Operations Networks, which is the part of ICAO Trust Framework. John is also a co-founder of the joint AEC IATA Electronic Flight Bag Forum. Please join me now in welcoming John, who will host our today's track dedicated to the digitalization of flight operations. And I'll give my seat to John. He will be presenting from this spot.
Thank you very much, Irina. Quite an introduction. I'm very pleased to have a number of speakers to join our event today. Firstly, I'm just going to cover a few tracks on the flight operations in the flight operations scenario. With the screen you just saw, the topics to be discussed will certainly not be. That's not the exhaustive list. We're only merely touching on several features that would be of great interest to the group. The speakers that I have lined up are not only top of their field. I could also say with confidence, they're my friends. We've worked together for Peter and myself. Peter, Reinhardt, and Jens have worked with me for a number of years, and it has been nothing short of a pleasurable experience to be exposed not only to their graciousness and kindness, but also their limitless expertise and passion for their various subjects. So I'll start with the first speaker. Peter Grau and myself have been working very diligently over the past number of years in the area which he will present, which is aircraft connectivity. However, the real empowering piece of that is the work that has been done within the EFB forum, and that's where the connectivity piece comes out. So if I'll just say a few pieces about Peter's role. In terms of this conversation, one should take into consideration the work being done at the EFB subcommittee, which is to develop standards applicable to EFB and thereby by extension connectivity. Peter and his team have been instrumental in working with the FAA for AC-120-76. I gather the ECHO is to come out soon, and the EASA AMC 2025. Just to let you know, the ARINC standards are comprised of hardware and software specifications as they apply to interfaces, application control, wiring and connectors, and data protocols. So, Peter, I hope that was a satisfactory introduction to what you present. The floor is yours. Peter Grau.
Thank you, John. Much appreciated, and I think you went a little overboard there, but I appreciate the compliments and the kind words. John and I, as John said, we've been working together for many years on the EFB Users Forum, which is an airline community-driven conference. We run 2 of those per year. I'm also responsible for a number of other committees within ARINC, aeronautical databases, global aircraft tracking, and timely recovery of flight data, as well as the EFB subcommittee that John just mentioned, formerly the Cockpit Display Systems subcommittee, which I just turned over to one of my colleagues a couple of months ago. Before we get into the presentation, I'd like to mention one other thing, and that is that ARINC runs between 20 and 25 different subcommittees, and at the present time, there's 6 of these committees that are involved very heavily in enabling connectivity in some way or fashion. And I'll run through those briefly later on in the presentation. So next slide. So a little bit of quick trip down memory lane of history of communications in aircraft. You know, the first flight was commonly acknowledged to be the Frenchmen, the Montgolfier brothers. Etienne was the first human who actually went up in one, but before he even was allowed to do that, King Louis XVI mandated that animals had to go first to see if they could survive. So on the very first flight of their hot air balloon, they had a lamb, a duck, and a rooster, and they survived. And then after that, people started going up. So what did they use for communication back then in 1783? Hand signals, signs, and torches. Of course, the first heavier than air flight, everyone knows the Wright brothers, Orville Wright, flew at Kitty Hawk in 1903. Two-way radio came along in 1915. And then, of course, you had the famous Charles Lindbergh transatlantic flight, first crossing in a single hop. That was in 1927. Radar came along in the mid-30s. And then the first commercial jet transatlantic crossing happened in 1958. Air traffic control system was developed in the mid-50s. And then here, an important milestone was development of ACARS. And that stands for Airlines Communications Addressing and Reporting Systems, developed by the airlines, still in use today, believe it or not. Although it's limited in its capability, it's still widely used, and there's been some improvements, of course, along the way. Other systems have come along since then. So we've got the Ka, Ku, and L-band SATCOM, Wi-Fi, 4G and 5G, etc. All of those things enable a connected aircraft, and those things in turn enable real-time data monitoring, big data, predictive analytics, and most importantly to us, improved operations. Next slide, please. So this is a slide that I pulled from a presentation that Mary McMillan from Inmarsat delivered at one of the EFD users forums in the past, and it gives you sort of a graphical illustration of how much the communications pipelines have improved over the years. So at the very bottom there in yellow, you see high frequency radio, 0.3 kilobits per second. Then you go into VHF, you're at 2.4, classic aero 10.5, VDL mode 2, which is what is commonly used today on radio 31, but you get into satellite swift broadband and you see the size of the pipe there, 432 kilobits per second. So greatly improved capabilities over the years. Next slide. I use this slide just to give you a feel for the amount of data that's being produced by aircraft today. So IVHMs, it stands for Integrated Vehicle Health Management. And in 2019, the last year before COVID, we had over 50% of operators using data analytics to compete. And the airlines are reporting between a 10 and 40% reduction in maintenance costs, 25% cost reduction in remote maintenance, that is, not having airplanes break down at a remote airport where you may not have enough maintenance or parts availability to repair it. And just to give you a feel for how the amount of data being produced has multiplied over the years, the A320 originally had 400 parameters monitored, about 50 megabytes of information per flight. Now we're up to 24,000 parameters, 12 gigabytes per flight. Move into a bigger airplane, the A330, originally at 200 megabytes, now 40,000 parameters and 30 gigabytes. And then now you look at the latest airplane, the A350, 600,000 parameters being monitored and a terabyte of information on every flight from 6,000 different sensors. So the amount of data that's being produced has greatly increased, and of course, that has implications for what you do with that data. Next slide. So some of the benefits that are enabled with connectivity, our overall goal is, of course, improved efficiency and safety. We're going to see more and more of 4D trajectory-based operations because of the crowded airspace. Proactive pilot decision-making, I'll get into that in a little bit more detail later. Flight path optimization, both vertically and laterally. For instance, winds aloft. If you have current winds aloft, you can better select your cruising altitude. That would be, of course, your vertical flight path optimization. Clearly, you want to maximize tailwinds when you can get them or minimize headwinds when you have to deal with them. Aircraft and engine health monitoring and in-flight predictive maintenance. So that's what I was just driving at in the previous slide. These capabilities are being expanded greatly, and connectivity, of course, enables those things. Reduce fuel consumption for a number of different reasons. But of course, if you have improved storm cell visibility, which is enabled by satellite weather, you can more easily plan your routing to avoid these things and avoid big detours that may not be necessary. So if you look at the typical radar, airborne radar, you may have about 100-mile range visibility with that. But you know, with today's aircraft, it may be as little as 10 minutes flying time, which isn't a whole lot. But if you have satellite weather, you know, that can be expanded greatly, and you have visibility for, you know, a couple 100 miles ahead. You can adjust your flight path accordingly, and then take a less circuitous detour. In addition, with satellite weather, you have, you know, a top-down view, which gives you a better feel for how deep these storm cells are, whereas your in-flight radar is only giving you a straight-ahead visibility, and so the depth of the storm cells is not very well illustrated. Of course, you know, if you have better weather visibility, you can reduce the contingency fuel that you need to carry for ETOPS flights. You have cost saving because you're carrying less fuel, less weight in the aircraft, so it's more efficient. And of course, you burn less fuel, so you have a smaller carbon footprint. Improve crew safety and passenger comfort. And I know some of the other presentations are going to talk about this, so I won't get into it in a whole lot of detail, but there's a lot being done in turbulence detection and avoidance. In addition, updated NOTAMs. On short flights, this isn't really a big factor, but on longer flights, you're talking flights 7 hours or more. Of course, situations change on the ground along with the weather. So if you have updated NOTAMs, which are enabled by connectivity, you can plan and adjust your flights accordingly. Telemedicine, this is something that isn't really talked about very often, but it does occur, and lives have been saved by being able to communicate directly with health experts on the ground until the airplane can land and bring a distressed passenger to better equipped hospital facilities. And then lastly, hopefully it never comes to this, but if it does, distress tracking and then timely recovery of flight data in the event of an accident. Next slide. So some of the challenges in enabling the connectivity, first of all, you need to have system resiliency with backup options if one of your communications channels fail. That should be pretty obvious, but sometimes you may be restricted to only one channel of communication, and you don't have a whole lot of choice. But wherever possible, you want to have multiple communication possibilities available to you. Now, you have non-complementary different communication systems. So what you're using at the gate, which could be gate link Wi-Fi or even cellular communications, your taxi time, and then of course in-flight communication systems. All of those are different, and a lot of work is being done right now to make these transitions seamless as you go through the different phases of your flight. Expense control. This isn't really talked about a whole lot, but it was a big factor initially. Airlines are starting to get a leg up on it now. But as I showed you before, the amount of data that can be transmitted from these newer airplanes is enormous. And clearly you don't want to be burning up a lot of communications channels and costs, either through ACARS or even SATCOM, transmitting just normal operating data. You need to winnow that down to be looking for, out of range and, poorly trending situations. So you're not just transmitting bulk data, which really isn't a whole lot of usefulness to the airline, assuming that everything is in normal operating ranges. So clearly you want to just focus on those things which could be problematic. Security, of course, this is a big one. And we talk about this every single time at the EFB Users Forum. You need to have malware prevention, detection, and reporting, system improvements to enable those things. And then, of course, normal operating process controls, things like whitelisting, limiting the number of users that are on the system, hidden SSIDs, things like that. Hardening of data interfaces, of course, and then, of course, testing of security controls that you have in place to make sure that they are detecting problems where they arise and then preventing further damage. And then lastly, and very importantly, of course, interoperability of all these different types of equipment on the aircraft and satellites and the ground. And the way we get there is with different standards. Next slide, please. So I'm going to run through quickly here the different subcommittees that are engaged in enabling connectivity. I'm not going to read through all of these things because it gets kind of wordy, but Data Links subcommittee, that develops and maintains standards that provide efficient transfer of aircraft, communication, addressing, and reporting system, that's ACARS that I mentioned before. ACARS over aviation VHF link control, that's AOA, and Aeronautical Telecommunications Network, ATN, data between aircraft and ground. So there's two, the ones that I have highlighted here, this subcommittee is responsible for a number of different standards. The two highlighted ones are being worked right now. ARINC 816, that's air-ground character-oriented protocol specification. That's expected to be completed next May. And then ARINC specification 631, that's a VHF digital link, the VDL mode 2 implementation provisions. That's also expected next year in December. 622, the one right before that, all these other ones that are unhighlighted are stable at the moment. They may be upgraded at various points in time as the need arises. 622 is the one that enables flight interval management, or FIMS, as you hear once in a while referred to from the acronym, where the airlines are able to assist in spacing their own aircraft. And this is really a big one, especially for the cargo guys, where you have a lot of airplanes coming into the same airport in a very short period of time. Next slide, please. So the Air Ground Communication Systems, or AGCS subcommittee, that supports air transport industry with air ground communications capabilities that accommodate character-oriented protocol like ACARS, and the newer bit-oriented protocols that are more efficient like ADS and CPDLC. That's cockpit to controller pilot data link communication. So this is where the ground instruction, air traffic control management can send instructions to airplanes through ACARS, and there does not have to be the normal broadcast and then read back by the aircraft pilots. That is always time consuming and ties up the frequencies. This is much more efficient. Of course, those instructions have to be agreed to by the pilot before they are accepted and implemented into the FMS. So there's two specs that are under update right now. Air characteristics 771 That's low Earth orbiting, or sometimes referred to as LEO. Aviation satellite communication systems. There's two supplements there, supplements 2 and 3. The first one expected May of next year, the next one May of 24. And this is the one that is governing the Iridium satellite constellation. So for those of you who are unaware, but the Iridium constellation, there's, I believe they have 31 satellites in polar orbits. There's 6 different planes. These satellites, they orbit the Earth about once every 90 minutes. And there's several satellites in each plane. So there's constant handoffs from one satellite to the next as a satellite moves into and out of range for the aircraft in question. Area characteristic 781, that's Mark III Aviation Satellite Communication Systems, supplement 9 for that. That's expected in May of 24. That one governs the Inmarsat constellation. And those are the ones that are out there in geosynchronous orbit. They're out there 22,000 miles out, something like that. And so the satellite always stays stationary over a single spot on the Earth because its orbital speed is coordinated with the Earth's rotation. So next slide. The Internet Protocol Suite, or IPS subcommittee. This one is leading standardization efforts to provide aeronautical telecommunications network, ATN, IPS safety services to the aircraft. And this defines a transition path from the ACARS, which has been around since the 70s, to a more modern ATN OSI, or Open Systems Interconnection Services, as the end state. So there's two specs underway right now. Report 658, it's Internet Protocol Suite for Aeronautical Safety Services. That's a roadmap. That's expected in May of next year. And then specification 858, the IPS Protocol Suite for Aeronautical Safety Services, and that's also expected next year. Next slide. There's a KU, Ka-band satellite KSAT subcommittee. That one's developing standards for broadband satellite systems and aircraft installation provisions. There's 3 specs underway right now. ARINC 791, which is KU, Ka-band communication systems for physical installation on the aircraft and its interfaces. 792 is 2nd generation KU, Ka-band satellite, and that's also due in May of next year. And then 792A is multi-modem KU, Ka satellite communication. So this one will allow switching from one satellite constellation to another. And it says fiber optics interfaces included. That's due in May of next year. Next slide. The Network Infrastructure and Security, or NIST subcommittee, that develops standards for secure broadband equipment interfaces, digital signature, and a roadmap for introducing IPv6 into aviation. There's 2 specs underway right there. 822 is Gate Link Wireless Security, and that's due in October of next year. And then project paper 811, that's underway, that's a new spec. That is due in May of next year. Next slide. So future possibilities. I did not go through the EFB work that John had discussed earlier. I think he did a very good job of kind of briefly summarizing it. There's a lot of work being done in the EFB subcommittees. That is what we do with all that connectivity once it's on board the aircraft. But I think this is mainly, this seminar is mainly focused on digital aircraft connectivity, that is aircraft to the ground. What the EFB subcommittee is doing is what we're doing with all that connectivity once it's on board the airplane. And there's a lot of work being done there too, but I won't go into a whole lot of detail on that. Anyways, overall, our long-term goal is, of course, sustainability. You're going to hear a lot about that, and already have. More timely departures and arrivals, fewer flight cancellations. Reduce fuel burn. Of course, that's a big one. reducing our carbon footprint. Airplanes drink gas, we all know that. So anything we can do to reduce the amount of fuel burn by choosing more efficient cruising altitudes, optimizing descent points, and optimizing our lateral and vertical flight paths is going to help. IATA, of course, you know, has a long-term aspirational goal of net zero by 2050. And that was established last October in 2021. We've got a lot of work to get there. It is feasible, but it will not be easy. Of course, improved safety and passenger comfort. We talked a little bit about that in Turbulence and avoiding storm cells with satellite weather. And then lastly, of course, more efficiency means lower prices and more competitive ticket prices. That pretty much wraps it up. I understand we're not taking questions here, but they can be emailed in and we'll address those. So thank you for the opportunity, John, and look forward to hearing from you.
Thank you, Peter. That was quite an education. Very concise. And just privately, I owe you one. We were grinding it out last night, so I owe you one, and I'll remind you next time I see you that I owe you one if you forget.
Okay, John. Thank you.
Thanks very much. Our next speaker is Reinhard Thanhauser. And before I give his intro, a little bit to Reinhard's character. He's the only person I know who likes to come to Canada for vacation in January. Quite incredible. Certainly a more stronger constitution than me. I would much prefer sandy beaches and palm trees, but to each their own. So without further ado, Reinhard is with Lufthansa Systems. He's a performance and ops engineer, and he began his engineering career with ARINC 424, data loads, and FMS charting. And he also developed aeronautical databases. He changed his position within his engineering to gather functional requirements for the Lido flight planning system and he supported projects that went forward with that. Since 2010, he's been working within the aircraft performance environment and responsible for Airbus aircraft in the Lido Airport Optical Database. And throughout his career, he's set up a special focus in the usage of digital aeronautical data sets like AIXM, digital NOTAMs, and ETOD. Reinhard, and lucky for us, he's the current chairman of the IATA Data Working Group, Digital Aeronautical Data Exchange, as an active member of several AIXM, Aeronautical Information Exchange Model working groups, and is an advisor to IATA at the ICAO Information Management Panel Working Group A, who we were lucky to have him because we had a meeting this morning that we couldn't make. So Reinhard, without any more words from me, it's you're on board.
Okay, I hope you can hear me now. Thank you very much for this kind invitation, this very funny invitation and this funny introduction. Yeah, I have the pleasure today to talk a little bit about AIS and AIM, what it is and how aeronautical data comes to the end users. When talking to other people not involved in aviation, I very often have the impression that our industry has a reputation of being highly sophisticated and always using the latest state-of-the-art technologies. And then I'm usually showing those people know them. Well, you know what I'm talking about. The last change to the NOTAM format, as far as I know, was done in 1982. That was the year when the Walkman entered the market. And I'm well aware that some younger people in this audience might not even know what a Walkman was. So what is AIS? The answer is very simple. AIS is a state responsibility. ICAO requires the states to establish an aeronautical information service and to provide products to publish aeronautical data quote from Annex 15 that are needed for safety, regularity, and efficiency of air navigation. So I already mentioned it. Annex 15 is the document that we are talking about. And Annex 15 has some supporting documents like the PANS AIM and the AIS manual that gives guidance and provisions to the states about the form and the content of the publication. So content, that's easy. That's what is part of the AIP, what should be published. And nowadays it's more or less, it's called a data catalog. It's a long list of attributes and objects that should be published by the state. And the form, yeah, that's also very easy. Right now it's more or less paper or PDF, which is basically also paper. And but we are luckily in the transition of getting more and more data on a digital way. AIS, or the main responsibility of AIS in the end is to collect data from their originators and publish them as printed AIP supplements and NOTAMs. I will talk a little bit later about this. And for all information that is relevant for flight operations that is not part of the data catalog, not part of the AIP, we have the mechanism of AAC to inform users about this. So you're already showing the next slide here, the legacy process. How do data get to the end users? And this is a very simple diagram of what we used to have up to a couple of years ago. So we have somewhere on the left side the real world that provides us a lot of data. And I already said that the AIS responsibility is to collect all these data. And what they would have done is just entering the data into their systems and maybe even just documents and providing these documents to the end users, to us. So we had a lot of manual data entry, and I can tell you we are still getting a lot of AIPs, aeronautical information publications, that are still Word documents, more or less. So it's not really streamlined. The products that we used to get from AIS are the AIC, the AIP and its amendments, the AIP supplements for short-term temporary data, long-term temporary data, and the charts and AIP documents in the combination. Is that what we refer to as a printed AIP? Yeah, in the end, what we get as end users, and the end users on the right side are mainly data houses, are the airlines, of course, and not to forget the pilots as the very end users, let me say it this way. So we are getting a lot of documents, a lot of paperwork from the states, and we are doing the same work again. We are reading the data, we are interpreting data, entering data into our systems, and creating products, our products that will be sent to our end users. That's FMS data, that's charting, that's flight planning, briefing, of course, that's aircraft performance data, and all the other related products. And I already mentioned it, I said one word, we are interpreting data. And that means we have a big break in the data chain, because sometimes the data that we're getting in these printed formats are not really understandable, are not comprehensible, and they are ambiguous. We have to interpret, and that's a big danger. That's actually an insufficiency of the old legacy process. And luckily, ICAO recognized this, and they saw a need for change. Next slide, please. Okay, The current system now is based on what the 16th edition of Annex 15, which was published in 2018, gives as provisions. And what we see here is a more streamlined process on the left side, and we see already some databases and interfaces, which means that all the AIS products should at least be generated from the same source. So where we had different documents in the past, we should have now still the same documents, but with the same content from the same source. And there's another significant change on the product side of the AIS world. We have digital data sets. For the first time, the 16th edition of Annex 15 allows the publication of data sets, digital data sets. And these digital data sets may even replace their printed, the printed version of the data. Right now, ICAO defined 5 different digital data sets. One is the AIP dataset, which is basically a dataset for flight planning, where we have all the nav aids, we have airport data, runways, airports, we have all the en route data, airways, airspaces, and so on. The second obstacle set is probably the easiest one. It's the obstacle data set, which is basically what we have now in the AIP, the aerodrome obstacles and the en route obstacles. And the third one is instrument flight procedures data set that will contain all the flight procedures in a coded form. And then we have a terrain data set that's more or less a digital elevation model, and the airport mapping data set. The first 3 data sets are already pretty well developed. The terrain data set and the airport mapping data set, they're still work in progress for the definition what they should contain and how they should be published. What all data sets have in common is that they should be based on an established common data model. In case of aeronautical data, this could be AIXM, Aeronautical Information Exchange Model. In case of flight procedures, this could also be AIXM. In case of terrain, we would probably use a common digital elevation model like GeoTIFF or one of these formats. Airport mapping dataset, I'm sure that there are several standards already on the market. Speaking about AIXM, as I said, is the Aeronautical Information Exchange Model. It tries to model the real world and to structure data so that the data that we get are unique and easy to parse. AIXM is governed by Eurocontrol and the FAA, and the good thing is that there are already coding guidelines as Eurocontrol specifications around for the AIP dataset and for the obstacle dataset. They can be used by the states to code their data and to publish the dataset soon. And luckily, right now, the first states are starting to publish not only obstacle datasets, but also AIP datasets in a digital format. If you look on the right side, there is no dramatic change on the consumer side. We still have the same products. We still have more or less the same process. But as we are getting more and more digital data sets now, the role of the data maintenance officers will change. They will probably not do so much typing anymore in the future. They will be more checking data. And then that leads, of course, that data also has to be corrected on the right side. We cannot be sure that all the data are always correct that we are getting from AIS and they are matching to each other. So the data maintenance side on the data integrator on the airline side will be more checking data for correctness, for consistency, and then correcting wherever necessary. Still, if you look at this picture, we have the classic NOTAM. The classic NOTAM is still text format and not related to anything else in the process. So next slide, please. Thank you. The ICAO Information Management Panel assigned the Working Group A, which is the Aeronautical Working Group of the IMP. They assigned us with the task to develop a NOTAM replacement system that integrates with digital data. So now we really see some more changes on the left side. We still have everything produced out of the same database. And there's another icon here that is called OPREP. We have more or less two digital variants of the data in the future. One is the digital data sets that I talked before, that they are available today already. And they are published on a regular basis, probably the ERAC cycle, and they contain planned and permanent changes. The OPREP, that's a working title, it's not final, it's a concept still, would replace NOTAMs and supplements. It would contain all temporal information, be it short-term or long-term. The important thing is that the OPREP messages, they are digital messages following the same data model as the data sets, and they are linked with the data set. So they are based on the baseline data that is already available in the data set. So if, for example, we have a temporary change to a navigate, or we have a change in declared distances on a runway, the OPREP message would refer to the UUID of the runway in the digital data set. And there's no interpretation needed anymore because we already know what the change in the OPREP actually affects. So for us, on the data integrator side, this makes things very easy because we only have to import digital data sets and OPREP data and bring them together. Of course, we will have data maintenance still. We will have to check the data. We will have to do quality assurance and corrections wherever necessary. These responsibilities will not change on our side. But the good thing is, once we have digital data sets and OPREPs available, then we don't need to check all the other sources anymore, because digital OPREP and data sets will replace all the other AIS products. Still, we see a NOTAM here as a product on the AIS side, and we see a NOTAM database. We need to have this for backwards compatibility. There might be some user groups that are still dependent on classic text NOTAMs. The difference is that the NOTAM database in the future should be more or less a mirror of the AIS database, and they should be generated from the OPREPs. So a future text NOTAM will be in parallel to the OPREP. And when we are importing OPREPs into our database, we can be sure that we have all the same information that is spread by NOTAM. In the end, we have less breaks in the data chain than we have today or had before, because we have a more consistent data chain from the originator side to the end user. You see multiple interfaces here, by the way. So we would be able probably to interface to other systems. States can communicate with each other using exchange model or direct interfaces. And of course, OPREP, the concept of the new digital NOTAM, is an enabler to bring information into the cockpit, into the EFBs. Right now, you all know it, we have a lot of textual information, and it's the pilot's responsibility to analyze the content of the NOTAM and to see what is affected. In the future, with digital NOTAM, we would be able to bring the NOTAM directly to the EFB. We could show a closed runway on the EFB. We could show a warning message, even if it's not related to the flight itself, but sometimes we have warning messages about grass cutting activity. This could be just an annotation to the airport, and you would see it at the airport and not in as a message in your big briefing package. And of course, the digital world would also enable us to filter data, to sort data in a way that we can have contextual information for the end user, which is the pilot in the end. So a favorite example would be if you have an in-flight emergency, there are probably different information that you are interested in. If you have a technical issue, then you would probably choose an alternate where you have maintenance facilities available. If you have a medical emergency, you would probably land at an airport where there's a hospital in the area. And if you have a real serious emergency, you're probably interested in firefighting categories. So this concept of digital data enables us to bring contextual information to the pilot, exactly that information that is needed during the particular phase of flight. So next slide, please. Yeah, this already concludes my presentation with a short summary. We are in the middle of the transition from AIS to AIM, from the paper-based world to the digital world. ICAO still has the same role. They are requiring the states to publish aeronautical information in accordance with Annex 15. Annex 15 is further developed and the guidance material is further developed, so we can be sure that all the new concepts will be reflected in the supporting documents. And ICAO gives provisions and guidelines for the states how to implement these changes. The role of AIS will also not change much. They are still collecting data from their data sources, and they have to publish the data. But in the future, we will see a transformation from the paper world to the digital world. So AIS will code the data according to the data model and bring the data to the end user using SWIM services. They will provide the data using the services. And of course, AIS still has to take care about that aeronautical data is always up to date. And as I said before, supplements and NOTAMs can be replaced by OPREP in the future. Yeah, this is basically a short introduction into the AIM world. If you have any further questions, I will be more than happy to answer them. On the next slide, you find my email address, or just ask the question in the chat, and I'll be happy to answer your questions. Thank you.
Thank you, Reinhard. Very interesting stuff. Certainly, we've done a lot, and we still have a lot to do. Thanks very much for your commitment in this area. So our next presenter is kind of where all these topics we've just discussed meet each other at the crossroads. We talked about aircraft connectivity. We talked about aeronautical information management. Without those two, this topic, trajectory sharing technologies, even the concept is not possible. Without the connectivity, and of course, without high quality data, high quality information, we can't do these things such as trajectory sharing technologies and the platform therein. So our next presenter has the task of kind of rolling all this out and concluding this part. Jens Gessing started off flying the CRJ series, and then he worked his way up to the A320 family, and he's currently the senior first officer on the A330, A340 at Lufthansa. Presently, he's part of the Lufthansa EFB team, and he's working on a whole host of projects involving EFB systems, avionics, and connectivity. And he's also been instrumental in various elements of some CESAR projects. And right now, his big focus is data exchange between Lufthansa and various ANSPs, air navigation service providers. So here we go with trajectory sharing technologies presented by Jens Gessing.
Yeah, thank you, John, and thanks for the introduction. Yes, I was smiling when I heard Reinhard's presentation about the NOTAM, because I would love to have the digital NOTAM in flight, because if you just look on the NOTAM for some major airports, you will know what I mean, because sometimes you cannot just comprehend what the information is about a NOTAM. And Peter's work actually as you said, made it possible to have all this information, like in-flight weather, turbulence, even analyze satellite pictures on the EFB possible, and it's really great to have it. So yeah, as you said, we're working, or I'm going to talk about trajectory sharing technologies here, a little bit about some that are already in place or will be mandated or will be introduced soon. The concept we introduced to IATA and the industry just before Corona. So if you could just go to the next slide. Yeah, why should we exchange trajectories? Why don't we just go fly the flight as it has been filed? And the reason is pretty simple, because the plan changes right after execution. So the first, if you could just advance to the slide, the first point that somewhere in between, about a few hours before the flight, the flight plan will be filed, and then the responsibility is handed over to the flight crew, and at that point, the flight crew decides on the amount of discretionary fuel, which actually is the first change of the flight plan. Irina, could you just hit space, and it's just minor animation in the slide. Irina? Yeah, thank you. So the flight plan is filed at a certain point. The responsibility is changed, is handed over to the flight crew. The flight crew decides on the discretionary fuel, which is the first change, and then at some point, the aircraft is or the flight is ready to commence, and at that point, probably the rate has changed, or the timing has changed, because maybe the apron is congested, or some other delay happens. Like as you know, many of you fly, it's a baggage offload just before off block, which means about 10 more minutes delay or more, which means the plan that has already been filed a few hours before isn't valid anymore. And then Irina, could you just advance, please? Yeah, another one. Sorry. Yeah, that's what I said. Go ahead. And then due to the changed weight, the aircraft may be not able to reach its assigned flight level in the flight plan, or gets higher, or it cannot reach a certain point which has been planned before in a certain altitude because of stronger headwinds, or it's earlier because of stronger tailwinds, or it has to circumnavigate any thunderstorm, and various other reasons make changes or causes change of the flight plan. So all in all, if you stick to a planned economy or a fly as filed concept, it's we lose efficiency in the airspace system, because as every flight changes or normally has a little change in the flight. That means that the plan that has been calculated hours before, and the plan for the entire system isn't valid anymore, basically. And if we could exchange the trajectories for the flights, we could raise the efficiency again. Could you advance to the next slide, please? Just go. Yeah, another one. Go ahead. That's not a good slide. Yeah, go. Just another one. Go ahead. 2 more. Okay. And 1 more, please. So just to give you an example, this slide is an evaluation of the planned takeoff weight versus the actual takeoff weight of the A330 fleet of Lufthansa from January to July 2022. And as you can see, the takeoff weight that has been calculated, or the actual takeoff weight, significantly deviates from the calculated takeoff weight or the planned takeoff weight in the flight plan, an average of almost 2.4 tons. And the interesting thing is that the highest negative deviation was almost more than 11.8 tons, and the highest positive deviation is almost 21.6 tons. And that is mainly caused because of payload changes, like more or less freight or more or less passengers, or the amount of discretionary fuel as decided by the flight crew. The problem here is that the flight plan will only be updated if the zero fuel weight, not the takeoff weight, that means only if the load increases by more than 3 tons, and only if this results in a change of the flight plan itself, based on the new weight but minimum fuel conditions. So the discretionary fuel, as decided by the flight crew, isn't taken into account at this point. Next slide, please. And what the result of that is what is shown here. This is an actual analysis of an ANSP with just a sample A320 flight. You can see the green line. The green line is the planned trajectory according to the flight plan. The orange line is the prediction of the ANSP based on their performance model of the aircraft on an assumed takeoff weight, not the actual takeoff weight, and probably not the one that's in the flight plan. And the blue dotted lines is the actual radar plot, which is in between. So as you can see, as the flight plan is usually based on a lower weight, it's most of the time it's too optimistic. And the prediction, because it's of the ANSP, because it's planned or based on based on average values, it's either too optimistic or too conservative. And the radar plot or the actual flight performance is somewhere in between. And I marked the level offs during this climb from 10,000 to about 30,000 feet. And there are 7 level offs in this climb just because of missing or an inaccurate prediction of the flight path, which is a point where we could raise the efficiency just by exchanging data. Next slide, please. So what is the solution? There already is a project implemented called the extended flight plan format, which is or will be used soon for filing flights to network manager of Eurocontrol and for ATC units. And this format actually will have more detailed trajectory data and as well aircraft performance data. So that should be enable the ATC units to better predict the traffic and their sector load and the entire traffic situation in the specific sector. And what you can see here on the screenshot is the old format. That's the item 15 of the flight plan. This is just the basic vertical profile. And in addition, in flight, there are some technologies that are currently available for some aircraft, like ADS-C EPP, which basically is an FMS downlink of the flight of the FMS or flight plan data with the current predictions based on the current conditions. And in addition, modern EFB systems can calculate the most optimum profile for a flight, independent of the original flight or flight planned vertical profile. And can reduce fuel burn significantly. And if you look closely, you can see the green, on the lower right, you can see the green profile, which is the most optimum one, and compared to the white one, which is the original planned one for that flight. And as you can see, the aircraft was probably lighter, so the entire profile shifted up, which is more efficient for that flight. Next slide, please. So as I said, AIDA-CEPP, it's automatic dependent surveillance contract extended projected profile. It's basically an FMS downlink. So data from the cleared flight path along and prediction data of the clear flight along the clear flight path, like times and weights. Currently, it's only available on A320, a family aircraft, since 2019. And right now, about 90 aircraft of the European fleet are equipped mainly from Air France, British Airways, Iberia, EasyJet, and Wizz Air. And Maastricht is the only ANSP right now that is operational for this technology since May of 2022. However, it's mandated to be introduced at latest at the end of 2027. So it will definitely come. Next slide. So in addition, just before Corona, we introduced the concept to IATA and the industry to use the flight profile optimization tools available on most of the EFBs, which are able to take into account the current weather, like winds and temperature, like Peter said as well, the current weight, actual weight of the aircraft, the current center of gravity, and other company-related factors, like let's say connecting passengers to get the most optimum profile for this specific flight. And the concept is called direct intent downlink, which basically is the downlink of this optimized trajectory to ANSPs via IP or data link. And I can happily say that the EFBs of Lufthansa are mostly connected via ACAS or IP. So this is a key technology to enable the direct intent downlink concept. So next slide, please. So why did we introduce the concept to IATA? The concept is, or as various airlines have different kind of optimization software on their EFBs, there are different export formats of the trajectories. So the idea is to have a central storage point for the data, so there's no need for a direct airline ANSP connection, but to have a central data storage point with a standardized export interface. And as we learned at that time, IATA had gained experience with such kind of infrastructure with the Turbulence initiative. So we asked them to help and ask about their opinion. And of course, IATA is, and which is a major advantage, is independent of a single airline or a region like Europe. Next slide, please. So some example use cases which seem to be simple, like this one, the first use case, the update and confirmation of first flight level on departure. So most times, at least in Europe, controllers are gonna ask the air crew for their first intended flight level, because they simply cannot have to confirm the numbers that have been filed in the flight plan before, because as I said before, the weight often changes. And in this example, you can see it. The green line again is the most optimum profile, or the one that is possible, and the white one is the one that has been filed. So there's a difference, and ATC usually is unaware of those changes. And if you had this direct intent downlink technology, you can send this information just after off block when the weight of the aircraft is 100% sure, instead of asking just a few minutes before the actual flight level has or is reached by the airline, so by the aircraft. So the ANSP, the ATC controller, can plan ahead using this information. Next slide, please. The next use case is the indication of step climbs and step descents, mainly for North Atlantic flights, because the ANSPs there, they plan ahead a lot, and they simply or usually don't have an idea when an aircraft intends to climb somewhere on the Atlantic. They have the flight plan, but they know that the flying pitch changes, And so they cannot plan ahead until the ATC or the aircraft actually sends a request for a change in flight level. So again, if ATC had the information that a certain aircraft intends to climb at a certain point at a certain time, they can plan ahead and make this profile possible, which in turn increases efficiency again and reduces fuel burn. Go ahead. Next slide, please. And the next sample use case, sector entry times. We usually for an ANSP, they have a rough idea when a certain aircraft will enter their sector, but they don't know for sure. And sometimes they only get the information when the aircraft will enter the sector when they get an information from the previous sector. And the technology like the trajectory intent downlink can actually give this information hours before. And according to our test flights, this information is pretty accurate. We had one test flight 6 hours before the actual sector entry was on. The prediction was on time. The FMS at that point was several minutes off, as well as the flight plan. So we strongly believe this is another good use case for an ANSP to increase the planning and estimate the actual sector load in an actual and tactical environment. Next slide. So all in all, this almost concludes my presentation. We strongly believe in sharing trajectories between all these stakeholders, meaning ANSPs, ATC, the cockpit, and the OCC or the operations control center and hub control centers will enable anyone or everyone to get the most benefits and increase the efficiency as much as possible for a specific situation in the airspace and increase the usage of the airspace in order to reduce fuel burn and CO2 emissions. And that's it. Thank you very much. If you have questions, as Arina said, I'm happy to answer them. Just put them in the chat, please.
Jens, thank you very much for that presentation. Your conclusions were excellent, and no doubt we'll be receiving pressure from you, Reinhard, and myself to get those digital NOTAMs online as quick as possible for you. So,
okay, it would be great. Thank you.
Cheers for that. Thank you very much, guys. And I'll hand it back over to Arina. Arina, it's all yours. Thank you, Arina.
Thank you very much. Our next presentation, and I think it fits perfectly the block with flight operations and our next track that we will start shortly about the air traffic management. So I'm excited to introduce you to our next presenter, Katya Vashenkova. Katya is the head of operations data solutions at IATA. She is responsible for developing global data sharing programs for flight operations, safety and sustainability areas of airline operations. Katya has joined IATA already 15 years ago and has worked on various projects to support the transition to digital operations with data shared across the industry. She's passionate about helping airlines create a safer and more sustainable operation environment, gain efficiencies, and maximize cost saving through data sharing. Please welcome Katya with the highlights on the IATA Turbulence Aware program. Katya, it's all yours.
So thank you very much, Irina, for introducing me. And today I'm going to talk about a very exciting topic that I'm sure most of you can relate to, being passengers. I'm going to talk about turbulence and introduce our Turbulence Aware program, which we started several years ago when airlines approached us as an industry association and an entity that helps to share data in a neutral way to help them share turbulence reports generated by the aircraft in flight. Next slide, please. So the industry is ongoingly trying to improve turbulence mitigation because turbulence is a pretty major safety concern. It is the leading cause of injuries to flight attendants and passengers, and it also generates a fair share of extra costs for the airlines, starting from the cost of injuries, extra fuel burn that is burnt in flight while trying to manage different turbulence encounters, and also creates brand damage when an airline has a turbulence incident, and it really speaks to the fear of flying of the passengers. So really there is a lot of activity in the industry to try and mitigate it. Next slide, please. The issue is that some of the most common current tools have limitations. For example, when a pilot reports turbulence, it is quite subjective and really is based on his own or their own perception of turbulence, its intensity, and it's hard to really take that as a major decision-making piece of information. Forecasts, as many of you know, can be hours long, not so accurate, can cover massive geographical areas. And then the weather radar is really great in predicting thunderstorms, but it's really not that useful when an aircraft is hitting clear air turbulence. So a lot of limitations and definitely a lot of room for improvement. And the problem is that a lot of research indicates that turbulence encounters will become more frequent and more severe in the coming decades due to the changing climate. So the industry, as I said, is looking for better ways to manage turbulence and mitigate the impact of it on the operation. So next slide, please. The good news is that there's been a lot of technological advancements in the last decade or so that is now enabling the aircraft to really measure turbulence in flight and send this objective automated data to the ground in real time to really help with turbulence mitigation using objective measurable data. Next slide, please. So what does it look like? Essentially, we now have an opportunity to look in real time at the report that shows us precise timing of turbulence, precise location of turbulence, and precise intensity of turbulence, which is really quite an innovative approach to managing turbulence and really complementing all these more traditional tools that the industry has been using for many, many decades. Move to the next slide, please. Yeah, so what is this turbulence measurement and the data that we're talking about? I'm not sure how many of you are familiar with the concept of EDR or eddy dissipation rate, but it is the official metric that ICAO is using for measuring turbulence. And what it shows is the state of the atmosphere around the aircraft in flight. Essentially, if you can imagine two boats in the ocean, one is a small vessel and another one is a massive cruise ship. When they hit a wave, they're both looking at the wave of the same size, for example, a 2-meter height wave. And this is similar to the EDR, which is measuring the height of the sea wave of the atmosphere around the aircraft in flight. So the equivalent of the 2-meter height wave can be EDR of, for example, 0.3. And the impact of the 2-meter height wave on the big cruise ship and the small boat will be different. And it's the same when it comes to EDR and the impact of turbulence of 0.3 to the aircraft of different sizes. The big aircraft such as Boeing 787, for example, crossing turbulence, which is measured as EDR 0.3, will probably experience light to moderate turbulence, whereas a lightweight aircraft passing through the same airspace where turbulence is measured as EDR of 0.3 will experience this as a severe turbulence. So EDR is an aircraft independent metric, but at the same time, the way it's impacting the aircraft is more subjective depending on its weight. So hopefully it sort of gives you an idea of how EDR works as a metric. The good news is that you don't really need to modify any hardware on the aircraft to implement EDR software. It is essentially an open source piece of software that can be installed on board the aircraft in the avionics bus, and it will start really measuring turbulence, and it's an implementation that does not require any certification or hardware installation. So the way Turbulence Aware program works is essentially the aircraft in flight on the aircraft where the software is installed is producing these reports as it flies, measuring both smooth air and turbulence encounters. It generates an ACARS message that is then downlinked to the ground servers. This is where IATA is picking up these reports from different airlines in real time. We then normalize the data, we do quality control of this data. We then make the data available as a data feed so that airlines can consume it through different third-party tools, through their own in-house tools, and as a data layer. And then we also make the data available through our own visualization tool, which is called the IATA Met Viewer. And the whole process between us collecting the data on the ground when the aircraft reported it and generating these reports as a global data set, as a data feed, basically takes less than 1 second. So it's really instantaneous. And the real-time aspect of it is really important because turbulence is not a phenomena that stays in the atmosphere for a very long time. So the more real-time objective measurements you have, basically the better decisions you can make in flight. Next slide, please. So here's a snapshot of our IATA viewer. I think it's important to mention that the data, the value proposition is not this viewer. It's really the data feed that can be used in multiple tools. And I will show you the list of the tools that have already integrated the data in a minute. But just to give you an idea of what the data looks like, essentially, here you see the last 4 hours of turbulence from 1 minute ago to 4 hours ago. The data can be filtered by the time of the report. It can be filtered by the flight level at which the report was generated. It can be filtered by turbulence intensity. And each report shows the location of turbulence, the report age. So for example, here it's 2 minutes ago. It shows the altitude, and it shows, of course, turbulence, the peak and mean values. And also, most importantly, it also shows the wind and temperature, which is the data that can be used to really maximize flight efficiencies and choose the most optimal flight level, and so on and so forth. And the other thing that I will mention here is these dots are really color-coded turbulence reports, and the gray reports are smooth air. Basically, it shows you where the air is smooth with confidence. And the reporting logic for this EDR is that every 15 to 20 minutes, if the atmosphere is smooth, the aircraft is generating the smooth air report, which is a gray dot here, to show that the software is working properly, but also to show where the air is really smooth so that the pilot can confidently climb to the most optimal flight level without affecting the cabin service, for example, or redirect the flight to a smoother, basically, area. And then when the aircraft is hitting turbulence, the data is generated every minute until the threshold goes down. So if you move to the next slide. So you saw the basically global data in the previous snapshot, and here what I wanted to show is that the data can be buffered around a specific flight path so that the pilot can focus on their own flight path and basically see whether turbulence will be affecting the flight and how to best adjust to it. For dispatchers, for example, they have these multiple flight paths that they can manage to essentially improve the experience and efficiency and safety of the flights that they manage. Next slide, please. So what you have just seen in terms of the data being integrated into our Met Viewer is also available in a similar way as a data layer and data visualization in multiple tools that the industry is widely using. For example, recently we have finished the integration into Jeppesen Flight Deck Pro. So it's available there for the airlines that are using those tools. It's available also in the EWOS suite, which is a product managed by SITA. Also, it's available in Flight Explorer by Sabre, Aftec, Flight Keys, and several other basically widely used tools by pilots, dispatchers. And we are continuously working with more and more integrators to make the data operationally available through different tools for the convenience of the airlines, because nobody wants an extra application, an extra window open to just look at turbulence. Everybody wants to have an integrated view of different weather layers or other operational data layers to have a comprehensive picture. So next slide, please. Currently, we have about 1,700 aircraft reporting the data, which comes from 18 airlines, and around 12 service providers have integrated the data feed into their tools. And we're collecting about 30 million reports per year, and this number of reports is growing essentially as we grow data coverage and implement more aircraft with the reporting capability. Next slide, please. So here you can see the airlines feeding data into the platform. Essentially, we have carriers from almost every continent. And if you go on to the next slide, you will see the existing data coverage over a 24-hour period. So a lot of the data is saturated over North America, Europe, and NATRAX, but we're really putting a lot of effort to maximize data coverage in Latin America, Africa, Middle East, and Asia Pacific. Next slide, please. Yes. So just to reiterate the use cases and how the data is really used operationally, a big use case is flight planning. So really comparing forecasts versus actual reports of what is happening in the atmosphere for now and how the flight plan might be affected. It is also used by dispatchers for flight following. If your aircraft does not have connectivity and your pilots cannot look at the data in real time in the cockpit, a dispatcher may send an ACARS message to prevent an encounter with severe turbulence, for example. And also the data is used by them to complement FIREPs that are being reported. If the data is available to pilots in flight, they use it to optimize the flight level, manage passengers and cabin, and then also safety can use the data for post-flight analysis and maintenance. Here, basically, you can see that major airlines are using the data operationally and confirming the benefits, such as saving injuries, saving fuel, saving CO2, and providing better service to passengers. And if you go to the next slide, that's really to reiterate the benefits in terms of improved safety, improved brand image and passenger experience, and most importantly, improving costs related to extra fuel burn and also reducing CO2 emissions as a result, especially these days when there is such an emphasis on sustainability. And it also helps to save costs on engineering inspections, which are mandatory if you report that you've encountered severe turbulence. So the data really helps to assess whether the impact was severe or if it was more subjective assessment. And some airlines have reported lowering insurance premiums. So this really concludes my presentation. If you do have questions or would like further information, please reach out to us on IATA@iata.org. And if you had questions during the presentation, I'll be happy to answer them following, post-webinar. So thanks a lot for your attention today.
Thank you very much, Katya. Appreciate. And I think it made a great introduction in our next part of the webinar. We are running a little bit late, but we'll try to catch up and still do a program as planned. For our next part, we're going to be looking into the air traffic management section. And with that, I'm very happy to introduce you to the host of our next section, which is also my colleague, Ruby Sayed, an aviation professional with 19 years of experience. Ruby is a holder of bachelor's degree in electrical engineering. She started her career as aircraft engineer with Royal Jordanian Airlines. Then she progressed from engineering to operational safety and management positions within the airline. She joined IATA Middle East and North Africa regional office in 2010, and then she joined IATA ATM infrastructure headquarters team in 2014. With her current role, she leads the ATM team with IATA, and she drives global ATM strategies and policies, including safe and efficient integration of unmanned aircraft systems into airspace. She is designated as IATA member to ICAO remotely piloted aircraft systems panel. She will be introducing our next presenters in the ATM section. So please welcome Ruby, who will host our next track. And with that, Ruby, I hope you are there with us, and I'll be switching.
Hello, everyone. Sorry for the delay. Just my laptop was not working for some reason. The mute button and the camera was not working. So with that, let's get right into it. So with this section, we heard from all the colleagues who were with us before about different elements for the future of digital aircraft operations. As we look into the future for the new aviation ecosystem, I can do it if you want. Yeah.
Go ahead.
If it makes it easier for you. All right, perfect. So when we look at the new aviation ecosystem, digital aircraft operations is actually, it fits into an overall type of operation where we look at, it's a digital consumer experience, it's a digital aircraft operation, it's a digital airport operations, it's also more digital applications on board the aircraft, and it's sort of also with this digital applications we are interconnecting the different modes of transportation together. At the same time, we are seeing that airlines are investing in automation and new aircraft technologies, and that is primarily motivated by different things, whether it's looking at efficiencies, environmental targets, or even modernization of fleets. At the same time, we have new and emerging players in the airspace that need to be integrated in the ATM system. And therefore, these types of new aircraft are also require different types of infrastructure, integration, because they have varying performance and automation. The problem that we see, and what both my colleagues will be talking about, is that we still have legacy regulatory frameworks around that hinder the, let's say, the effective integration into the airspace, into the ATM system. Over the years, airlines have continued to invest in new aircraft technologies on board, and yet we seem to just polish the ATM system here and there without really looking at a modernization plan, at revisiting some of the underlying assumptions and looking at it from a whole different perspective. So the two speakers with us today, Todd and PK, and if not known to you, then they're both very ingrained in a lot of activities about the future of ATM systems and about the integration of new types of aircraft and the new entrants into the ATM system and airspace. They will be talking about these issues in their presentations. We will start with Todd, and I'll just do the presentation of both of them right now, so that we'll go from one presentation to the other. So Todd is going to give us his perspective from Thales. He has a very rich experience looking at systems, at automation, at digital applications. And then we will hear from PK, who's known as PK with his initials for everybody in the aviation industry, from NASA, who will be talking to us about what they are doing, how they envision the future, and then what we need to think about moving forward. So with that, Irina, thank you, and I'll hand it back to you so that you can take us to the other presentations.
Wonderful. So I'll ask Todd to, there is Todd. Okay,
here I am.
We can see you, Todd, thank you. Just give me 1 second, I'm going to pull up your presentation.
So thanks, Ruby, very much for the introduction and the opportunity to join this webinar today. what I intend to talk about a little bit is about what's happening in the airspace, particularly around new entrants and what we see happening in the air traffic management business as we look at the technologies that are used to support air traffic management. If you can go to the next slide, please. The presentations that already happened in this webinar were in many ways a good introduction and a good framework for some of these challenges that are coming and some of the things that are impacting the industry. Could I have the next slide, please? Thank you. And so what we see is we see a lot of focus on how digital technology is coming into the industry, how it affects aircraft operations, airspace users. We have more complex mobility flows that are going to be coming because of new vehicles, new users of the airspace. We obviously see a huge focus on environmental footprint, on total cost of ownership, speed to market for new capabilities, as well as the regulatory environment. But one of the key things that we think will be happening is a move towards what we're calling defragmentation and virtualization of airspace. Next slide, please. And when we think about that, I like to use low altitude drone operations as as sort of an example of why we see this trend happening and where it's coming, where it's going to impact the airspace and all airspace users. We see lots of different ways in which new entrants are arriving to use the airspace and to deliver services and capabilities that were not really possible before, or were not done at the same economic efficiency that is possible today. And that could be transport of cargo, that can be inspections, that can be a variety of different applications, entertainment, security, et cetera. And all these users under most countries' laws are airspace users that have a right to use airspace as well. And the question is how do we enable that to happen? Next slide, please. Because most of the airspace has been structured historically to support what I call quote unquote legacy airspace users. So military operations, commercial operations, business aviation, general aviation, some helicopter operations. And so, the chart you see here is a very typical sectional that you would have that describes the airspace. With the classifications, you have a variety of airports, you have obstructions, you have international boundary there. This happens to be around the Detroit area. This airspace, in fact, is fairly static and inflexible. And it's designed to be, changes are happening on a quasi-monthly basis. And yes, there can be some TFRs and NOTAMs and things that may make some change to it, but it's not really designed to be dynamic and flexible and changing on an ongoing basis, which makes it very suited to high density scheduled aircraft operations into known airports. It makes it not very suitable for on-demand and unscheduled operations that may want to also share that airspace. And that's the challenge we have in front of us. If we go to the next slide, and I'm hoping this animation is going to work properly. It is good. We took some traffic data, and what you see is the animation is running through, basically slicing down from altitude, starting about 1,500 feet above the ground and going downward. And what happens is you look around an area like an urban environment, and with the airports around that urban environment, is that at a reasonable altitude and above, you have a lot of traffic density. So this is basically surveillance data, seeing where aircraft are located, where they're operating. And as you cycle through from a higher altitude to a lower altitude, we see that in fact, as you segment the airspace into smaller and smaller chunks, and you imagine the airspace at different altitudes, you can find places where the airspace is completely unused. And when we talk about capacity in the aviation system, in the airspace system, we talk about congestion, but a lot of the congestion really is at the airport and at the runway, but it gets extended into the airspace around that because of the terminal procedures, because of the accuracy in which aircraft can fly and ATC systems can track them. And so we believe that as we progress into the future, technologies are going to enable us to segment this airspace into smaller pieces and actually utilize more of the capacity of airspace, particularly for the new entrants who don't necessarily need to operate in and out of the same airports that that the commercial passenger and cargo aircraft are operating out of. Next slide, please. And so when we think about the air traffic management systems, these are systems that are largely monolithic, proprietary, and often in very specialized and bespoke configurations built for a particular air navigation service provider, for a particular country or airspace. And we're a provider of these systems, and we'll be the first to acknowledge that they don't migrate and evolve very quickly. And a lot of that is by design. A lot of that is as a result of the safety regulations and the things we need to meet. But it also is about human factors and training controllers, about inflexibility of the airspace, about the potential implications of changes, et cetera. And so as a result of that, it's a slow process for us to embrace innovation, to bring it into the market and to make it available. And as Ruby said, many of the air traffic management systems are effectively repolished versions of things we've been doing for quite a long time. Next slide, please. And we can look back to, and this was from the FAA Next Gen ConOps in 2007, so 15 years ago. And at the time, what we were saying is, okay, Next Gen should be delivering greater information sharing between the aircraft, flight operations, and ANSPs. And we saw some of the presentations earlier where we're starting to see some of that happening with trajectory exchange using data links and different commercial communication options in order to share that information. But this vision that was created 15 years ago, we're still quite a long way from having that truly broadly adopted, and we're seeing progress, but there's a long way to go. And I think that you can imagine this image on the right as being replicated multiple times for military operations, for commercial space launch, for unmanned systems that are in the airspace and other airspace users that will emerge. And so the question becomes, how do we create the technology platforms and capabilities to interconnect all these players and share the information that's required? Next slide, please. So we've been sort of looking at it from two perspectives and working it from two perspectives. One is a significant focus on the overall system architecture and the use of cloud technologies in order to enable these sorts of exchanges and interactions between stakeholders in the aviation system. And that's an important part of it. And then the other axis, we've been looking at specific applications and how we bring in artificial intelligence, machine learning, and other techniques to leverage all the data in the aviation system, which is largely underutilized, in order to improve decision-making, to optimize the use of airspace, and to facilitate better aviation operations overall. Next slide, please. So one of the core challenges underneath this, though, is this issue of safety and security. So by definition, the systems have to be safe. It's an unmodifiable foundation of the aviation system. But as we connect systems, we increase the threats from a cybersecurity perspective. The methodologies for doing cybersecurity well include monitoring systems, patching them regularly, making software upgrades. The approach we take for safety is to test the system and lock it down and try not to change it, because every time we have a change, we have to go through a significant analysis, testing, certification process. And so, we're really focused on designing new technologies and platforms and systems that are safe and secure by design, and that bring this ability to follow the best practices in cybersecurity, but still retain the level of safety that's required in the aviation system. Next slide, please. And that's where we see some of the challenges. We need to evolve our safety paradigm. We need to work on how we regulate these kinds of technologies, how we look at acceptance and adoption of the technology that's used to manage the airspace by ANSPs and other users, and how that linkage to aircraft and other airspace users and operators is changing. And we need to look at how the role of the air traffic controller is going to evolve over the long term, so that we're in a position that you know, the next 15 years from now, we actually have reached the point where many of these concepts we've talked about for a while are becoming more embedded, and we've accommodated all the new entrants who have an equal right to utilize the airspace as the existing users that are in the airspace, but do it in a safe and secure manner. So with that, I will be happy to take any questions offline afterwards, and I'll turn it back over to Ruby.
Let me cover for Ruby now. So thank you very much, Todd. It was very concise but very contentious to my view. And I think just to progress on our time, as Ruby has introduced our next speaker already, we will place larger and more detailed bios in our materials after the webinar. But I'm sure you will be very excited to listen also to our next presentation, which is PK from NASA. PK, I can see you. Can you see us, hear us?
Okay, can you see and hear me?
Yes, we can hear you now. So just give
Okay,
me
thank you.
one little moment. I'll pull your presentation.
Thank you. Well, while we are waiting, I'll basically thank you for inviting me for this event. It's really important to start thinking about it in the broader context of how things are going to change. So I'm going to cover what the future airspace operations could look like. This is a view, this is not the view. Based on the lessons we have learned, of course, for decades in doing research in air traffic management, but also in the last 10 years of unmanned aircraft system traffic management. So next slide, please. The main premise I would like to offer is that we need to ensure that the airspace system is ready when the vehicles are ready. In the past, we have been a bit of a reactive mode. We did a lot of upgrades starting from 60s, obviously, and we'll talk a little bit about that. However, now things are evolving at much rapid pace in terms of the new types of vehicles and the diversity and density, and we need to ensure that the airspace system moving forward is going to be ready to accommodate the vehicles that come on board. Next slide, please. Okay, so here is what I mean by that. You know, when I said why we need to change the paradigm towards, you know, ensuring that we are much more proactive, is we are looking at above common line. There's going to be satellites and space assets, so space traffic management there. But then below that, in Class E airspace, we have a number of new entrants coming up: supersonic, eventually hypersonic balloons and hail and such. Then we have Class A airspace that is going to get penetrated through more basically commercial space launches, and then we come down to E, B, C, D, G. Is basically you'll see a lot of drones and urban air mobility, and of course in some places the launches will go through that. All of these are interesting in itself because the performance characteristics of different vehicles are now quite divergent and not cohesive, and that requires a lot more thought in terms of how we are going to accommodate them and interoperate them without too much interference on each other. Obviously, in some cases there will be, but in many cases we want to try to build a system such that through proper information sharing and collaboration, we would reduce the need for interference to each other. So next slide, please. Yeah, so the big picture is, I think we owe to society, in my personal opinion, this is PK's personal opinion, that the aviation reach has to to go to every zip code in the world. Why? Because I think it has a true power of enabling us to go anywhere. 1 mile of road takes you only 1 mile, but 1 mile of aviation land can take you pretty much anywhere. That's the fundamental, uh, basically, power of aviation we have. And obviously, we are making significant changes in aviation. It's the noisiness is going down, the speed is going up, and many other things. We have more challenges now as a result with sustainability, but aviation's reach is getting broader and farther. And I think this can be really pivotal for the entire society to change the paradigm. We'll talk a little bit about that in the next slide. So as a result, we see need for integration in the airspace is going to only keep growing. Next slide, please. What's likely to happen is that, if we are truly successful in aviation, then you can imagine that we don't all have to go on the same road to the same place to work. We can have businesses and houses spread out much more, and aviation can take you places rather than the road taking you to only central business districts, or you have to stay closer to the highways and roadways because that's where transportation takes you. I think the transportation is fundamental limitation in the way the societies are structured today. So that's sort of the big picture thinking. If we are able to unleash the aviation potential in a way that will basically allow us to spread and much more integrated greener living, then we have a very powerful society that we can look forward to. However, to get there, we have a number of challenges. One of them is the airspace systems, obviously. So the second enabler for that is the new technology. So I think Todd talked about this a little bit, IoT, digitization, AIML, electrification, certification, autonomy. What's interesting, though, the interesting observation here is that these things are coming largely from outside of aviation. But those things, those developments, the convergence of these technologies have significant impact on aviation. And we have not yet taken into account those to its fullest extent. And it's basically convergence of all these technologies to see how we can modify the airspace system at large and aviation at large. Third is obviously, we talked about this, is the number of types of vehicles and the density and the tempo and all of that is going to look dramatically different. And it's a chicken and egg. If we build better aviation, air transportation system, airspace operation system, then that will enable further growth. So we want to be enabling the growth and not be, basically be the barrier for growth. Next slide, please. Yeah, so we tried basically this kind of a setup in a very small baby step through unmanned aircraft system traffic management. One that is much more currently, Class G airspaces where we started 10 years ago. You can see it's going to other places. A bunch of deliveries, public disaster, public safety, disaster relief, and all of the use cases for small drones. And small drones, why it makes sense is that it actually allows us to rapidly test different ideas. Of course, it has its own limitations in terms of size, weight, and power, but we can try out a number of things in a little bit less risky manner. So that's why we focused on UTM, below 400 feet in the early stages, but then we learned some significantly insightful lessons. Next slide, please. So one of the things that I'll share here is the type of lesson we learned. Basically, what we think, or PK thinks personally, is that the architecture that we set up for UTM that allowed us to have a federated system really scales well. It allows us to take best advantage of industry's capabilities and not monolithic, basically, ways of doing things. We want to do service-oriented architecture. We want to have third parties, possibly in some cases may not be third parties, but at least having service-oriented architecture, and each service it accelerates and transforms in itself rather than having this monolithic platforms where all services are bundled together. then it reduces the innovation option for each service. So I think the fundamental premise here is that having service-oriented architecture, having possible role for third parties, going towards cooperative, and by that I mean share and care of each other, so sharing the trajectories with each other through the intent sharing application protocol interfaces, which haven't been done before, and everything going through digital means and integration of air and ground capabilities allows us to get to that management by exception paradigm. Currently, the paradigm that we have in air traffic management is management by permission or management by clearance. And the reason for that is only air traffic control system has the complete information. Now, back of this is that by digitizing, by creating a cooperative structure and service-oriented architecture, we can share that information to every actor that wants to operate in the airspace. Once you have the information that's shared, then now you have ability to go towards a different paradigm. One rather than depending on one entity to make every decision, you can have basically operators make those decisions, either supported through third parties or by themselves. But idea is to get towards management by exception through a federated system. And that's kind of what we learned from UTM, that it seems to work. We still have a lot more work to be done in this category to see how it translates everywhere, but I think it's showing extremely high promise to get to this architecture. Next slide, please. So here is basically the evolution that we see what's likely to happen. So Epoch 1 was early stages, as the birth of air traffic management started, air traffic control after Grand Canyon accident, 1950s, late 50s. And focus was on safety. It was all procedural, basically deconfliction, and it's based on estimate of aircraft positions and the current planned position as well as current position. Then came along the radar, where we could know the exact position of the aircraft, and then we can estimate it. Then came the 4D trajectory, which allowed us to estimate the planned positions a lot more tightly in 4 dimensions. So that's when we started to increase we become more proactive and increase efficiency. Then the next step is, in case of FAA, it's the infocentric NAS, is collaboration, but because we're connecting all the information sources and allowing, basically third-party services to provide possibly some examples. And then going towards service-oriented architecture allows us to scale a little bit more. However, that alone is going to increase efficiency. It may not allow us to get to that scale that we are expecting in the future. So this is where we need machine-to-machine interactions and automated systems in a way that will allow us to scale that. Now, there are a lot of research questions there. My statement there doesn't mean that we have proven that it will 100% work, but if we get to that point, then we can scale and we can have scale-free growth that is likely to basically support the societal needs as we move forward. Backbone of all that is, of course, digital transformation, and you saw some of that in Todd's talk as well. Next slide, please. Okay, so here's sort of interesting thing that we have learned from what happens in the current air traffic management service. We have all services provided by ANSP, whereas in the UTM-inspired model, we have some services provided by ANSP and some are by third parties, possibly. That distinction changes based on which country and their policies and such. So we won't touch the policy aspect, but we can say that the technology will allow us to provide third-party services if a country chooses to. But currently, humans address all off-nominal situations, whereas we need to try to move towards as many situations as possible that can be handled by automation. And that's when we can gain the system, basically scalability. Currently, we depend on humans because off-nominal and contingencies need to be managed by them. When we have that kind of a responsibility on them, then they need to have a complete situation awareness, and they need to be in the loop. And when you have them in the loop, then you're dependent on their mental gymnastics, which they do an amazing job. but you cannot overload them. So that has a physical barrier on the capacity. And I think if we want to unleash the true capacity, we have to figure out which basically situations of nominal contingencies can be offloaded to the automation in a safe manner. And that's where one of the research angles is very critical. Also, currently very little interaction happens among users and third parties, and I think having the interaction with the users and third parties and having that cooperative, collaborative managed airspace operations would significantly reduce the burden on this basically air traffic control system at large, and then allow us to basically let the users decide what is optimal, ideal for them. Another aspect of current system is human is at the epicenter of information integration. If we can try to get the automation be the epicenter of information integration, then we gain significant, again, basically workload reduction on the people. But all this is to get to focus. I'll say one more thing here is that we need to focus on total system performance. So right now, it's basically safe, expeditious, orderly flow. That's the order. First safety, then expediency, then order. Now, while that model is really great and works well for a system that is managed by humans, and that is the right thing to do, that doesn't allow us to have simultaneous growth and scale, efficiency, sustainability, all these parameters that we talk about. This is where the automation comes in the picture. The total system performance is what we need to focus on, saying, how do we ensure that safety and scalability and sustainability angles all simultaneously taken into account, which is beyond our cognitive basically limitations to try to do that. This is why automation becomes important. And again, using the paradigm of third parties and cooperative and digitization, we allow ourselves to migrate towards a management by exception paradigm rather than management by clearance paradigm. So our role in NASA is basically figuring out how we're going to do the research, what kind of requirements, performance requirements will be on a technology that is focused on total system performance. Next slide, please. So again, I will leave this thought in that if we truly want to scale, then we need to reduce the burden on the humans. They do a tremendous job, but because we put so much burden on them, their workload has to be watched so that the safety doesn't suffer. And if we can unleash that some way figure out how to move from management by clearance to management by exception by all this digital information that we have, that should allow us to basically make decisions using the automation and the digitized format rather than a central system. So if we can get to that federated system, we can unlock the true potential. And that's when we can get to airspace system is ready when the vehicles would be ready, kind of a paradigm that I mentioned right in the beginning. Next slide, please. So fundamentally, I would like to propose that we should focus on total system performance as our goal. And we need to embrace the innovation in aviation at the same time respecting the safety tradition. And I think we can do this by good bit of research, collaboration across multiple entities, industry, government, and organizations like IATA and ICAO, all together to chart the path towards the total system performance. So here, this is my last slide, and I'm happy to take any questions online or on email as well. In my email is provided here. Thank you again for inviting me and NASA to this event.
Thank you very much, PK. And this will conclude our today's track of Digital Aircraft Operations webinar. Again, I would like to quickly reiterate that you can drop your questions in the question tool. We will answer them for sure, and we will send you the answers and questions all together in the file. And you will receive also the recording of this webinar, which will be placed most probably in one of the IATA official social media channels. And the last word, Tomorrow we will meet at the same time, at the same place, to continue our webinar on 2 other tracks, which will be technical operations and cybersecurity in aviation. So thank you very much for attending and staying a little bit longer. We unfortunately had a few technical problems, and I hope I can all see you tomorrow, and we will have 2 other wonderful tracks as we had it today. So have a nice rest of the day wherever you are, and see you tomorrow. Bye-bye.